Hello everyone, we are Sarah, Yusra, and Albatul, and we're going to present our project on smart and sustainable waste management. The core problem lies in how waste is currently handled. Most waste sorting systems today are either manual, which makes them labor-intensive and highly prone to error, or semi-automated. They are efficient, but they're still limited in accuracy, especially when dealing with mixed or contaminated waste. And as a result, the recycling rates remain extremely low, and large amounts of the recyclable materials end up in landfills. Another major issue is that even the existing systems are mostly not scalable and cannot be implemented in real-world applications. So simply, the existing solutions are not efficient, not intelligent, and not sustainable enough for modern urban environments. And this is what motivated our work, that the manual sorting cannot keep up with the complexity and volume of modern waste streams. At the same time, cities lack real-time monitoring systems, meaning that overflowing bins often go unnoticed, and this has caused pollution, health risks, and even environmental damages. Our motivation is driven by the three key goals: improving recycling efficiency through intelligent automation, reducing human dependency in waste sorting processes, and supporting the development of smart, sustainable cities. And these all align with the global sustainability goals, particularly responsible consumption and production, and the sustainable urban development. Now, in recent years, research in waste management has increasingly focused on the use of deep learning and computer vision to automate waste classification. And many advanced models, such as the convolutional neural networks, have demonstrated very high accuracy values, in some cases even exceeding 90%. And this proves that AI can effectively identify different types of waste. And in order to further improve the performance, many studies have applied data augmentation techniques, allowing their models to better handle variations in the shape, color, or even the lighting conditions. And yes, several systems have been successfully deployed on embedded platforms, and this shows that there is potential for having real-time, low-cost waste classification in practical environments. However, despite these advancements, there are many key limitations that still exist. Most, most of the existing solutions focus only on the classifications without integrating real-time monitoring or system feedback, and others struggle with real-world conditions, such as mixed or contaminated waste. And most importantly, many systems are not fully optimized for scalable deployment in smart city infrastructure. And building upon these observations, our work aims to go a step further. Instead of focusing only on classification, we propose a system that combines accurate AI-based sorting, real-time bin monitoring, and integrated hardware control. This creates a more complete and practical solution for the sustainable waste management.
The way we designed our system is the first step being capturing and processing. So we place the waste on top of the platform and we press the push button, which triggers the camera to start image capturing and processing. The second step is classification and sorting. So the trained AI model will look at this captured image and it will classify it into either recyclable or non-recyclable. Based on this classification, the platform will tilt and it will sort the object into its corresponding bin. The third step is bin monitoring. So our sensors will continuously monitor the bin and it will check the bin fill status and it will update it on the dashboard. So for our models, we initially used a model that we trained using Teachable Machine. The dataset consisted of 170 images with two classes, being recyclable and non-recyclable. And each class, we divided the images into training and testing. Here on the left side, we can see samples from our recyclable and non-recyclable classes. So then we went on to improve our model. We trained a new model using the MobileNet V2 architecture, and we chose a dataset that had 15,000 images. This dataset originally had 30 classes, but we combined all the similar classes together, and we ended up with 12 classes in total. We chose this dataset because it had lots of different images and lots of different classes, so the variety was good for this AI model. So the classes ranged from plastic, cans, paper, glass, cardboard, clothing, coffee grounds, eggshells, food waste, shoes, styrofoam, and tea bags. And for each class, we split the images into 60% training, 20% validation, and 20% testing. Here on the left, we can see a snippet like a few images from the dataset from each class. When choosing our hardware components, we wanted to pick components that are both high in performance and energy efficient. So we used the microcontrollers Arduino Uno and the Pi 5, and our other components included the Pi camera module 2, which we mounted on the wall of the model. We used a servo motor that we placed below the platform to tilt it during the sorting process. We used a push button that when we press it, it triggers the camera to start capturing. We used two ultrasonic sensors, one for the recyclable bin and one for the non-recyclable, and they both measure the bin fill status. And we used three LED indicators: green meaning that the bin is not full and that we can continue sorting, yellow for the bin being half full, and red for the bin being completely full. So this is how our live monitoring dashboard looks like. We have color-coded bin status, which is going to be green color if the status is normal, yellow for half full, and red for full status. We also have real-time bin fill indicators, which types OK for the normal status, half for the half full, and full for the full status. We also have recyclable and non-recyclable item counts. So every time an item is sorted into its corresponding bin, the counter for that specific bin increases. For our bin fill level logic, the bins that we used, we measured their heights, and based on that, we decided on the distance for each status. So for the normal status, if the distance between the sensor and the waste is greater than 18 centimeters, the green LED turns on, which means that you can continue sorting. If the distance is between 10 and 18 centimeters, the yellow LED turns on, meaning that the bin is half full, and the green LED turns on, meaning that we can still continue sorting. If the distance is less than 10 centimeters, the red LED turns on and the platform stops tilting, and we notify the user that the bin is full and that we cannot continue sorting.
Let's move on to the results, starting with the evaluation of the model performance. So for our initial model, which was done on Teachable Machine, we actually had a very high confidence of around 99%. However, that was an indication of overfitting because we used a very simple dataset and model. And this high accuracy was only during testing, but in the real world, it would not be able to handle the diverse waste items. This takes us to our second model that we trained on MobileNet. We can see in the first graph that the accuracy values increase over training epochs and the loss values decrease in the second graph. This indicates the stable learning of the model. We can also see that in the performance metrics, which are the precision, recall, and F1 score, which achieved around 85%. Moreover, the confusion matrix further confirms the high classification accuracy of our model, where we can clearly see the diagonal pattern in the matrix. And of course, we have some limited errors because of the visually similar categories. Here, we see the complete operation of the system. So first, we place a water bottle, which is obviously a recyclable object, and then we can see how the system correctly classifies it into recyclable and disposes it in the correct bin, and also the correct LED lights up. Then we place a non-recyclable object, such as a pen, and again, the system classifies it correctly, disposes it into the correct bin, and displays green because the bin was still empty. We can also see in the dashboard that it displays the status for each bin. So when a bin becomes half full, it becomes yellow, and when it's full, it becomes red. And we can also see the count of numbers in each bin. So this helps us get updates in real time. To conclude our work, we developed a smart IoT-based waste sorting system, which enables automated and real-time waste classification and monitoring. The system contributes to a smarter waste management by improving recycling efficiency, reducing the dependence on landfills, and also supporting cleaner and more sustainable urban environments. In fact, a solution like this has the potential to reduce landfill waste by over 40% and significantly lower overall waste generation. Looking ahead, our future work will focus on deploying the system in real-world environments like campuses and public spaces, as well as scaling it for integration into smarter city infrastructure. We also plan to implement cloud-based monitoring for centralized analytics and also improve the system's robustness for outdoor operation and energy efficiency. And lastly, we want to expand the classification to handle multiple waste categories so it would be more practical and have an impact on a larger scale. So those are the references we use. And lastly, we want to thank you for watching this presentation.